Hello! Welcome back to the next rubber duck physics video. Tamási A.4 here. Today we are diving into the most challenging part of rotational dynamics, solving some epic problems that combine everything we have learned so far. These problems will test our understanding of torque, angular momentum, equilibrium, and rotational kinetic energy. So, drop off your coat, roll up your sleeves, and don't worry, our rubber ducks will be here with us to help along the way. First, let me introduce the three problems we'll tackle today. We have the bucket in the well, the disc falling onto a rotating disc, and the ladder at the wall. Let's start with the bucket in the well. Imagine a bucket tied to a rope, unrolling from a cylinder as it descends into a well. This setup might sound a bit abstract to us now, but for our great-grandparents, this was an everyday sight. The bucket could be drawing water up, or it could be lowered. Many of them drew water from a well manually by using exactly this mechanism. We know those parameters we could normally know about the well: the mass of the bucket, small m, the mass and size of the cylinder, capital M and R, and, of course, gravitational acceleration. I also let you know that the moment of inertia of a solid cylinder is half of its mass times its radius squared. From these, we'll determine the linear acceleration of the bucket sinking. Let's solve this step by step. Let's write Newton's second law for the bucket, taking the up direction as positive. The sum of forces, T minus small m times g, equals small m times a, where a is the acceleration of the bucket and t is the tension in the rope. For the cylinder, we can write Newton's second law for rotation. Tau equals I times alpha, where I is the moment of inertia of the cylinder and alpha is the angular acceleration. The torque here is caused by the tension in the rope, which equals T times R, where R is the cylinder's radius. Now, because the rope is tight, the linear acceleration and velocity of the bucket must match the linear acceleration and velocity of the point on the edge of the cylinder where rope loses contact. This will be crucial in linking linear motion to rotational motion. That's why we can connect these equations and solve them at all. Finally, we also have to make use of the fact that for the points on the edge of the cylinder, A equals alpha times R, as we know for any kind of accelerating circular motion. From these, we can solve for the angular acceleration alpha of the cylinder and then find the linear acceleration of the bucket as it lowers. Not making the video longer, with dictating all the maths, we end up with acceleration equals small m divided by small m plus half of capital M, and this fraction multiplied by g. You can clearly see that the fraction is a number, less than 1, and acceleration of the bucket is less than if it were falling freely. Do not be misled by the idea that it is because of friction at the axle. We didn't take the torque from friction into account in any way. Yes, even if an ideal well, if it exists, in which the cylinder is completely frictionless, the bucket will accelerate less than when dropped, because a set part of its gravitational potential energy is now continually being used to do work on the cylinder by angularly accelerating it. If you want, you can easily find the angular acceleration of the cylinder by substituting back into the equation connecting the accelerations. Now let's move on to the disc falling onto a rotating disc. Imagine a spinning disc, and then we drop another disc on top of it, not necessarily the same size or mass, whose axis is in the same line as that of the spinning one. Of course, I would like more to drop a non-spinning rubber duck onto the first disc, but the moment of inertia of the duck, which has no rotational symmetry, is quite difficult to find, so we stay with the second disc. The two discs stick and end up rotating together, but it's not as simple as it sounds. This is very similar to what happens in a collision in linear motion, where two objects collide and stick together. Just like in a linear collision, there are certain things that make this situation tricky. Let's start with some parameters we would normally know of two disks: the initial angular velocities of both disks and their moments of inertia based on mass and radius. Again, half of mass times radius squared. We need to figure out their combined angular velocity after the collision. Can we use conservation of energy to find the final angular velocity? Take a moment to think about it. The answer is no. Why? Because when the disks make contact, friction does work, and thermal energy is released, which means some mechanical energy is lost, the exact quantity being unknown. So conservation of energy won't help us here. Instead, we need to use conservation of angular momentum, just like how we would use conservation of linear momentum for a sticky collision. Newton's laws would be too tricky here, because the contact forces change unpredictably during the collision. We rely on conservation principles instead. The principle here is L initial equals L final, where L, the angular momentum, equals I times omega. So we have I1 times omega 1 plus I2 times omega 2 equals I1 plus I2 times omega final. Omega 2 equals 0, therefore this term disappears. Then we can rearrange to find omega final. Notice that this is like an inelastic collision. Some energy is lost, but angular momentum is conserved. When I say energy is lost, I mean mechanical energy, of course. From here, we plug in the values and get the final angular velocity of the two disks equals I1 over I1 plus I2 times omega 1. The fraction is, again, a number less than 1. The two disks are going to spin together slower than the falling disk did. Take delight in this beautiful result for a short moment. Then, for our final problem, we bring out the ladder to the wall. Imagine a ladder leaning against a wall, touching the ground with a frictional surface. The question is, what's the minimum coefficient of static friction required to prevent the ladder from slipping, given a certain angle between the ladder and the ground? Again, we'll start with natural parameters that can be known about this arrangement: the mass of the ladder, its length, the angle it makes with the ground, and we are looking for the minimum coefficient of static friction that ensures the ladder doesn't slip. For the ladder to stay in place, it needs to be in equilibrium. This means the sum of all forces and the sum of all torques must both be 0. What's great is that, when calculating torques, you are free to choose your axis. It doesn't have to be the axis of rotation. Moreover, in this problem, there is not even a fixed one. It's often practical to pick an axis that makes the torque of at least one force 0. In this case, using the point where the ladder touches the ground is a smart choice because it eliminates the torque due to the frictional force and the normal force at the ground, two torques at once. Let's sum the torques around the base point. The torque due to the gravitational force is tau gravity equals m times g times L over 2 times cosine theta, where m is the mass of the ladder, g is gravitational acceleration, L is the ladder's length, and theta is the angle. The torque due to the normal force from the wall is tau wall equals n wall times L times sine theta, where n wall is the normal force exerted by the wall on the ladder. We balance these torques. One rotates clockwise and the other counterclockwise, so we take their difference to be 0 to find the normal force from the wall. N wall equals half of m times g times cosine theta over sine theta. Now let's consider the forces acting vertically and horizontally. Vertically, we have the gravitational force pulling down and the normal force from the ground pushing up. Horizontally, we have the frictional force at the base and the normal force from the wall. Since we are in equilibrium, we know the vertical forces must balance and ground equals m times g, and the horizontal forces must also balance, F friction equals n wall. And we know about the nature of friction that it's proportional to the normal force at the contacting surfaces, in this case at the ground, by F friction equals mu times n ground, where mu is the coefficient of static friction we want to find. Combining these equations, we substitute the normal forces and solve for mu. Mu equals n wall over m times g. By plugging in the value of n wall that we found from our torque equation, we get mu equals m times g times cosine theta over m times g times 2 times sine theta equals half of cotangent theta. So, the minimum coefficient of static friction to prevent slipping depends only on the angle of the ladder. If mu is less than cotangent theta, the ladder will slip. Kind of unexpectedly, the limiting value of mu doesn't depend on the mass or the length of our ladder, neither on which planet we set it up through the value of the gravitational acceleration in case we found a vertical wall on that planet. Take away the thought that it's meaningless to ask what's the moment of this force without specifying about which axis. Torque is always dependent on the axis chosen. We have explored 3 different problems, each showing different aspects of rotational dynamics. The bucket in the well, connected linear and rotational motion. The falling disk emphasized conservation of angular momentum, even in the absence of conservation of mechanical energy. And leaning the ladder helped us understand equilibrium conditions. With rotation, you can think in terms of forces and torques, or energy and angular momentum. It's about knowing when to use which approach, and we have practiced both here. Congratulations on completing this video playlist on rotational dynamics. You have tackled some truly challenging concepts, and I hope you feel much more confident in your understanding now. If you are still thinking about it, you might want to ask yourself, what if the ladder was on an incline instead of a flat surface? How would that change things? The ducks congratulate you with a ceremonial squeak. Thank you for joining me on this deep dive into rotational dynamics. I hope these problems helped you see how to connect the concepts learned in real-world situations. If you found this helpful, don't forget to like, subscribe, and share your thoughts or questions in the comments. Need more help? I am available for tutoring online. Check out the Rubber Duck Physics channel's description for details. Thank you for watching, and see you around.